Game theory begins with the recognition that in strategic environments, each player's optimal action depends on the choices of others. This mutual dependency creates a loop. Your best move depends on my move and vice versa. Simple optimization which treats the environment as fixed falls short because the environment is actually shaped by the player's own decisions. This is why equilibrium reasoning, such as Nash equilibrium, is essential. It requires that each player's strategy is a best response to the others, creating a self-consistent outcome. Rationality alone isn't enough. If players hold incorrect beliefs about others, even rational choices may not align and equilibrium may not emerge. Thus, both rationality and belief action consistency are necessary for stable, predictable outcomes in strategic settings. Structure of a game, when moves are made and what information is available, can dramatically affect outcomes, even if the normal form, the list of strategies and payoffs, is identical. Sequential and simultaneous games may look the same on paper, but their dynamics differ. In sequential games, credibility matters. Some Nash equilibria rely on threats that aren't believable if the subgame is actually reached. Subgame perfection refines Nash equilibrium by requiring optimality at every stage, eliminating non-credible threats. This highlights the importance of timing and information sets, which are encoded in the extensive form but lost in the normal form. As a result, two games with the same normal form can have different sets of subgame perfect equilibria, showing that informational structure is crucial for dynamic consistency. Strategic games, beliefs about other strategies are just as important as the strategies themselves. A player's best response depends on what they believe others will do, and those beliefs must be consistent with the actual strategies chosen. If beliefs and strategies are specified separately, inconsistencies can arise, undermining equilibrium. True equilibrium requires a fixed point. Strategies generate beliefs and beliefs justify those strategies. This is especially important in games with incomplete information, where Bayesian consistency ensures that beliefs are updated correctly based on observed actions. Without this consistency, equilibria can be supported by implausible beliefs, leading to unstable or unreasonable outcomes. Thus, the joint determination of beliefs and strategies is at the heart of equilibrium analysis. Iterated elimination of dominated strategies, IESDS, is a powerful tool for narrowing down possible outcomes in a game. However, it relies on more than just individual rationality. It requires common knowledge of rationality. Each player must know that others are rational, know that others know this, and so on. Without this recursive knowledge, players might keep dominated strategies out of fear that others could act irrationally. Nash equilibrium, every player's strategy must be a best response to the others. Strictly dominated strategies can never be part of a Nash equilibrium, as they always yield lower payoffs. This distinction between individual and common knowledge of rationality is key to understanding why some strategies are eliminated and why Nash equilibrium is a robust solution concept. Randomization in equilibrium, such as in mixed strategies, arises not from a love of chance but from the need to remain unpredictable. In games like matching pennies, being predictable allows opponents to exploit you. By mixing strategies, players keep opponents indifferent and prevent exploitation. In mixed strategy equilibrium, a player must be indifferent among all strategies in the support, otherwise they would shift entirely to the best one. Furthermore, many games have multiple equilibria, which creates prediction challenges rather than solution problems. The theory doesn't always select a unique outcome, so additional criteria like history, expectations, or learning are needed to explain which equilibrium is likely to emerge in practice.